In the Can We Do That video released before this video, we showed where the exponentials come from when you're trying to solve second order differential equations. But today we're going to generalize that process to prove it. So let's get on with it. So let's lay down some ground rules of what it is we're looking at. We are going to be dealing with differential equations of the format you can see on the screen right now. A, B, and C are constants, but they're chosen so that b squared minus 4ac is greater than 0, which of course is to do, or linked with I should say, the discriminant of a quadratic, which is itself linked to the differential equation by the auxiliary equation which we usually use to solve these things. But then if we're dealing with b squared minus 4ac is greater than 0, that's one very specific scenario. Don't worry, we'll be dealing with the other scenarios, the other sort of cases we could deal with in another couple of future proof it videos, so do stay tuned for those videos as well. But if we're dealing with this specific case, then we already know the solution to this differential equation will be of the format y equals a lots of e to the power of the first solution to the auxiliary equation, lots of x, plus b e to the power of the second solution, lots of x. Because this is a prove it video, it's going to be quite algebraic. So if at any stage you're looking at what we're doing and you're not sure why we're doing it or how we're allowed to know that we're allowed to do it, well, I'd recommend you take a look back at that aforementioned Can We Do That video, because we go through a more numerical example of the process we're looking at here today, which therefore makes it a bit easier to see why we're doing what we're doing at the various stages, and therefore hopefully makes it a bit more clear. But also, because this is a prove it video, I must give you the usual warning, which is... yes, the things we're doing in this video are things we're doing just for fun. You don't need to know them for exam. This is just a proof to satisfy our curiosity. But on top of that, not only do you not need to know the proof for the exam, but also the very method, the very approach we're using to solve the differential equation in this case is one that you shouldn't normally be using to solve a second order differential equation. Usually you should be using the traditional idea of a auxiliary equation, complementary function, finding particular integral, all that sort of stuff, because that's the quickest and most efficient way of doing it. And the reason we're doing it in a different way here in this video is because we're having to prove stuff, so we're having to go back to fully showing things manually, all that sort of stuff. But that's not normally the quickest, best way of doing these sorts of differential equations. Okay, with that out of the way, what do we need to know in order to be able to do this proof? Well, you need to know how to solve first order differential equations. You need to know how to solve them using separation of variables, but also you need to know how to solve first order exact differential equations. Those are the sort of ones where you use an integrating factor in order to be able to do the solution. But on top of that, you also need to be familiar with quadratics and how the roots of a quadratic, specifically when there's two real roots, are related to the structure of the coefficients in that quadratic. Namely, minus the sum of the roots is to do with the middle coefficient, and the product of the roots is to do with that coefficient that's on the end. That's a useful property that we're going to be making use of to help us rewrite some of the things we have in a few moments. Cool. So with that said, let's get on with the actual proof, and therefore the starting point would be our differential equation. We've got a, b, and c, which are real constants, but they're chosen for the purposes of this video so that b squared minus 4ac is greater than 0. Okay, the first thing we're going to do is we're going to divide both sides of the differential equation by a, because what that means is it means we've got one less coefficient to have to deal with, which makes it easier to cope with. And therefore now we can start using some of those properties we were just mentioning about quadratics. Even though we don't have a quadratic here, we know this differential equation is related to one by the auxiliary equation, even though we're not actually ever going to write out the auxiliary equation here because, as I said, we're doing this very manually here today. What we can do is realize the solutions of the auxiliary equation would be basically the solutions you'd normally get from the quadratic formula with coefficients a, b, and c. And what I'm going to do is I'm going to use those two solutions to split up that middle term, that middle coefficient that's in front of the dy dx, like so. which looks really horrible. But if you aren't happy with why I'm allowed to do this, then you can just try and confirm it by recombining these two middle terms I have. If you do that, you'll realize very quickly the square roots will cancel out because the minus and the plus in front of the two different expressions. And then that will leave me with the other bits combining to make a minus minus 2b over 2a, which does simplify to positive b over a, lots of dy dx. So we have everything that we had before. However, that looks really horrible to read. It was horrible to write out, so I don't want to have to write it out anymore. So we're going to do some substitutions to make it easier to do stuff going forward. And crucially, because b squared minus 4ac is greater than 0, these two things in front of the dy dx's are different values to each other. So that means I can define them separately. We could let p equal one of them and let q equal the other one of them, which is nice because it immediately means I can start writing the quadratic in a much more succinct way, and I don't have to just stop there because, as I said, those expressions that I've replaced with p and q are the roots of what would have been the auxiliary equation. The product of those roots would be related to the c over a that's in front of the y. So therefore c over a can be rewritten as p times by q. Again though, if you don't believe me, bit of homework for yourself, pause the video, have a go at multiplying those expressions of minus b plus or minus the square root of b squared minus 4ac all over 2a together. If you do that, you will just get a c over a, which is quite cool. It's nice that maths works so neatly like that, but therefore I am allowed to rewrite the c over a as p times by q. Nice! This is where the real magic now begins, because I can realize that I can factorize minus q out of the third and fourth term. So I'm going to do that. That'll leave me with a dy dx minus py inside the brackets. But then wait a minute, if you look at those first two terms, you'll realize those are just dy dx minus py differentiated with respect to x. So we could rewrite our differential equation to reflect that fact as well. And then we could do another substitution. Sorry, a lot of substitutions today. It's just to make it easier to see what's happening. So therefore, I could say let k equal dy over dx minus py, because that's that little expression I can see happening in two places inside this differential equation. But in doing so, doing that substitution, it now means this second order differential equation now just becomes a first order differential equation in terms of k. Nice, because that means it's actually very easy to solve. We can solve this one using separation of variables. So I'm going to move the qk onto the other side and then divide both sides by k to get this. Then I can integrate both sides with respect to x. That means on the left I effectively just integrate with respect to k instead, which means I get a ln k, and on the right hand side, because q is a constant, it'll integrate to qx and then add on an integration constant. Cool, plus c. So we could then try to rearrange to make k the subject of the formula by doing e to the power of both sides. And then we could start splitting up the right-hand side using index laws, because that plus in the power could be written as multiply with two separate bases. But as c is a constant, e is just a number, e to the power of c is itself just a constant. So therefore we could rewrite it again to tidy things up as a new constant. So let's call it, I don't know, d. So k is equal to d lots of e to the qx. Nice. So that's where we're up to so far, but we're not done, because we want to find what y is equal to. That's what the actual solution to the differential equation is. But good news, we already related k to y earlier. So therefore, we can write a new differential equation relating y to the expression we got for k just now. So this is another first order differential equation that we can solve, but now to find y. Unfortunately, this is one that can't be solved using separation of variables. We're going to have to solve it as a first order exact equation. Therefore, the coefficient in front of y is going to influence the integrating factor. As I said, I'm hoping you're familiar with how to solve first order exact equations. Minus p would integrate to minus px, so therefore the integrating factor is e to the power of minus px. Multiplying both sides of the differential equation by that integrating factor gets this. And again, if you're familiar with first order exact differential equations, you'll be aware that left-hand side is secretly just the result of what you get if you differentiated by the product rule the integrating factor times by y. So therefore, if I integrate both sides with respect to x, the left-hand side will just become the integrating factor times by y, and the right-hand side will also need to be integrated with respect to x. In order to help me do that, I've used index laws to combine the e to the qx and the e to the minus px, meaning I've got e to the power of q minus p lots of x. Q and p are just constants, so therefore it means when I integrate that thing, I'm just going to divide by q minus p, because that's how we integrate exponentials of that format. And then I'm also going to have to remember to include another integration constant because we have integrate again. And therefore, I've chosen to use the letter plus a because we've already used the plus c earlier in the worked example. Cool. So now we've done that, now I can rearrange to make y the subject of the formula. So if I multiply both sides by e to the px, that will isolate the y, meaning we end up with this. But all I've got to do now is a bit of tidying up. I realize that d's are constant, q and p are constants based on the fact they're in terms of a, b, and c, and a, b, and c were also constants. So therefore, let's rewrite that as its own new constant. Let's call it, for instance, b. And then the e to the q minus p lots of x times by e to the px could also be simplified using index laws. So, of course, as we're multiplying, that means we're going to add in the power. Also multiply it out the brackets with the q minus p and the x. And therefore, the minus px and the positive bx are going to cancel out, meaning we're going to be left with just y equals a lots of e to the power of px plus b e to the power of qx. P and Q are the solutions to the auxiliary equation. So that's why the solution to a second order differential equation that has two roots to its auxiliary equation will be what you can see on the screen right now. There you go. That's the proof. That's amazing. I quite like that. It's pretty neat. And therefore, be aware this is just one of 3 cases. We'll be dealing with the other 2 cases, as already mentioned, in another couple of Prove It videos, so stay tuned for those. But therefore, we are done. And therefore, all I can say is do check out some of my other videos. Like and subscribe because I've got lots of interesting videos like more proofs of various things in the maths and further maths A-levels and the Can We Do That series where I explore loads of really cool concepts further and beyond what you might have seen in the classroom. Goodbye.